Hello. Sai. Hello. 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 Check. Hello. Check. Hello. Check.
Hello. Hello. Check. Hello. Vasan sir. Hello. Hello. Check. Hello. Hello. Check.
Hello. Check. Hello. Hello. Sir, off చేసి ఆన్ చేయాలా?
Check. Hello.
So we also are having getting delayed.
Good afternoon, everyone. So, welcome back to the plenary talk organized under our conference. We have our speaker who has joined online. He is Professor Sven Groppe. Let me brief about him. He has received his doctorate degree in 2005 from University of Paderborn, Germany. He was a member of DAWG W3C working group,
Hello?
which developed the semantic web query language.
Seven?
He has
Yeah, please
publication
continue.
record that includes more than 140 publications in the areas of semantic web,
Seven?
query and rule processing and optimization.
Seven?
Big data, cloud and
Hello?
serverless computing. Peer-to-peer networks, Internet of Things, hardware acceleration via GPUs, FPGAs and QPUs, data visualization and visual query language. I request Professor to take over the session. Can you hear us? You are not audible. You are not audible, Professor.
You are not audible. Please check the audio video fix something. Please check your audio. Not audible. So all the participants are waiting. You are audible in my WhatsApp or not audible in the system. Can you check once?
So sorry for that, because I didn't get the response right here from directly in the Teams meeting. So thank you very much for the nice introduction right here. I hope you can see my screen right here. I hope so, that we can go on
Yes, your
further
screen is
with it.
visible, sir.
Very good. So we can now start. So my talk is about quantum data management and quantum machine learning for data management. I will briefly dive into the basics of quantum computing, because I guess that not all of you, or most, or even most of you, are not familiar with quantum computing, but it's a very, very, in the moment, a current hype, and it's a very interesting technology, which we should look into it. That's at least my opinion about it. So, the basics, and then later on I will give some details about, okay, what we can do for data management issues, what can data management do for quantum computing, and so on. So the basics are about quantum mechanics. So quantum mechanics, it deals with the physics in the atomic and subatomic scale right there, and that is very differently from the physics for objects in daily life, in our normal life. Now, there are some phenomena which are completely different. And of course, this must be considered right there for different technologies like transistors, lasers, nuclear power, superconductivity, and of course, it's also the basis of the quantum computers. On the other side, we already have many, many technologies for computation. You all know, okay, the multi-core CPUs. We have already much capable multi-core CPUs in our smartphones, laptops, servers, and so on. The next computational architecture, which has much more capabilities, is the many-core CPUs with a special form of GPUs. we might also look at FPGAs again, so fight programmable gate arrays, where additionally you have some interconnection network which you can freely configure. That's the point there, so that you can do or process some data pipelines. And now the computer right there is a quantum computer. And there, we have some phenomena which we can use from quantum mechanics, as I already told. I will give some brief details about it later on. We will also see that, or must consider that, not all what you can do with normal CPUs makes sense of a quantum computer. So what makes sense, for example, are mathematical optimization problems to solve them on a quantum computer. But at least for the current state of quantum computers, it doesn't make sense to process large data with it. You know, so at least for the current state of quantum computers. Maybe that change in the future, but in the moment it only makes sense, for example, to go on with mathematical mathematization problems to solve them. And for example, for data management, choose that maybe query optimization, concurrency control, there's something, transaction schedule optimization, which I will briefly detail on it later. So in general, we have, or basically we have two types of quantum computers. One is the universal quantum computer, which uses quantum logic gates arranged in some quantum circuit with which you can do computation. So we have here a circuit presentation on the right. And the other is quantum annealing. There, you can have some objective function, give it as input, and it is optimized. You can find the minimum of the objective function right there with quantum annealing. It's very simplified. Sure, it's now very simplified, but basically it can do the same as simulated annealing right there. But it is very simplified. So I have one question right there from the audience.
Yes, sir. I have a question. Can I proceed?
Okay, I can proceed. You have a question, but don't want to.
Can
say it right now?
I proceed?
Yes,
Can
you shortly.
Yeah. Sir, can you please explain about the difference between classical computing and quantum computing, or the
Yes,
basic
we
concepts?
On the next slides. That are on the next slides. It's very many slides right there. Please be patient for it. So the basic concepts right here. So for classical computation in the classical world, you have the binary digits, the bit. You know, there you have 0 or 1. You know, that is a information unit which you have in the classical computation. In the quantum world, you have the quantum bit, in short, qubit, and you have also some base states, 0 and 1, but you have additionally a linear combination of both states. You can have, you could say, states between quantum states. I show you later on some model for it. And then the basis, so I speak now about universal quantum computing first. The basis in the digital world, in the digital circuits, are logic gates, where you perform one or more bits to produce a single bit output. And in the quantum logic gate, you perform one or more qubits to change the quantum state of a single qubit. Here's some example. So we have a NOT, or also called inverter, in the classical world, having the symbols, and of course it switches 0 to 1 and 1 to 0. In the quantum world, you have the NOT operator, or also called Pauli X gate, where you have different symbols in the circuit representation, and it changes then the base states from 0 to 1 and 1 to 0. And also the probabilities from, if you have some mixture of the states, a superposition right here, a mixture, the probabilities of 0 and 1. So what the probability is before for 0 becomes the probability later on for 1 and vice versa. So we have also a model for representing at least 1 qubit states right here, the quantum state for 1 qubit. There are also representations for several qubits, but they are not so fine as for the 1 qubit. And you see that, okay, a quantum state is there a point on the Bloch sphere, on the surface of a Bloch sphere. You can represent it like this. And the base state 0 is on the North Pole, and the base state 1 is on the South Pole. Of course, in the quantum computer, you don't have Bloch spheres working. There are many physical approaches to implement quantum computers out there, but you can have this model to visualize and to think about the computation steps right here, which performs some manipulation of the quantum state. And we will see that you can think about operation just like some kind of some transformation, some rotation in the Bloch sphere. And most are reversible right here. There are only few which are not reversible, like the measurement, which is very important to get the final result, because you can't get the quantum state directly out of the quantum computer. You must always do a measurement. And what that means, we first look at it in the classical world. It's like this, a measurement there. You look into some kind of box, you could say, in which state your bit is in the classical world. Okay, there is no change if you look at it. So before the box is closed, you don't know in which state the bit is. You open the box and see, okay, it's 0 or 1 right here. For the quantum world, it's similar. And the state is not destroyed as in the classical world, if, but only if, the quantum state is in one of the base states. So 0 or 1, if it is before 0 or 1, the state is not destroyed. But it can be on any point in the Bloch sphere, and you can only open up the box and look into it, and you only can see, okay, it's 0 or 1, but maybe it's somewhere between. And some other state on the Bloch sphere, the quantum state right here. And if you, if you measure it, it collapses to 0 or 1, so the original quantum state will be destroyed. That's the point. But in this way, you only get information out of it, and dependent on which position your quantum state is on the Bloch sphere, there are some certain probabilities where it collapses to this base state, so 0 or 1 base state. You know? That means, okay, if it is more close to 0, then in almost all times it collapses to the 0 base state. If it is more close to 1, in almost all times it collapses to 1. If it is somewhere between, so on the equator right here, then it is half-half. Then it will be collapsed to 0 or 1 with equal probability. So this measurement was according to the z-axis. You can have also have measurements according to the other axis right here. Okay. And with this, you already have the first commercially viable application of quantum computation. And that is a generator for two random numbers. You just bring the quantum state in an equal superposition where the probabilities are like this, that it collapses to the base state 0 or 1 with equal probability, and you have your random number generator. But of course, we want more than just a random number generator. I already told you, okay, collapsing to 0, 1 is according to the probabilities. Is it more close to this or that base state? You can have measurements according to x, y, and z axis. And if you prepare your qubits quite often in an identical way, you have identical prepared qubits. And then you can do measurements according to the axis. And with that, you can get the information, okay, approximately which quantum superstate is it which you measure right here. You know, but that can be only done approximately. And you need quite many shots. It's also called shots on the quantum computer right here to get this information. You know, very often you have 1,000 shots or something, but typically it doesn't consume so much time. There's also another famous theorem. It's a no cloning theorem of one qubit. You cannot get, you can get, if you prepare the qubits in an identical way, the same quantum state, but you cannot copy the qubit right here and have it independent from the other, and work on that independent from the other, and then later on make a measurement and have there's always some correlation between the original qubit and the one which you copied right there. So that's the no cloning theory. So only not perfect copying possible of information in one of the X, Y, Z axis. Other information of superposition gets lost. But you can later on, we will see with the Keynote gate, you can use another technique right here. So the operations in quantum logic gates are that you do some rotation in the Bloch sphere. For example, the NOT operator right here. There you have some rotation about the x-axis. That's why it's called also Pauli X gate. And you flip the or exchange the probabilities for the 0 and 1 base state right here, which we already see. And it's quite easy with mathematics to describe, because you can express it with a rotation matrix and a matrix multiplication. Right there. I don't have an example for it, but you can just have the quantum state multiplied with the rotation matrix, which is given here, and from the input you get then the output. It's quite straightforward. And what you can see, okay, if it is here rotated around the x-axis, that it is mirrored right there, and then you can mirror it back. You will get the same quantum state again. Yeah, one more advanced quantum logic gate is the CNOT gate, the controlled NOT gate. So in the classical world, it's like this, that you have a control bit, and if the control bit is set, then it flips the target bit. You can have it also with the quantum states. So here you have the control bit, and the input and output doesn't change if the control qubit is in the base state 0, and if it is in 1, then it flips, and it also flips the probabilities in according to the quantum state of the control qubit. So if the control qubit, so if you have some probabilities for the control bit related to the input bit, then for the 0 base state for the control qubit, it remains the same. But if you have if you look at those multi-qubit inputs where you have one for the control qubit and one for the input qubit, then the probability change for it, that becomes 0 right here, but it becomes 1, 0, the probability for it if the control qubit is right given here, because or if you look at the probabilities for it right here. Okay, and it's also a reversible gate. That means that 2 applications of CMOD retrieve the original input again. Right here, you have a bigger rotation matrix because you have now 2 qubits operations. And with the CNOT gate, you can get so-called Bell states, where the output qubit is entangled with the input qubit. And that means that, for example, in this case, where here you have a 0 as input before the NOT operation, before the CNOT operation, and we have the input qubit A right here, then later on, you have 2 things. So one thing is you have the same probability for A and B, but for these multiple qubit together. So you will see, okay, if you measure the base state 0 at the A input, you directly get only it collapses also, then B collapses also to 0 right here. If, as I said, you measure 0 for the A input. And analogous for 1, if you measure 1 for the A quantum state, then you get also 1 for the B quantum state. You will not get some quantum state 0, 1 or 1, 0. That's not possible in this representation. You only get the results 0, 0 and 1, 1 for AB. Except maybe some noise are there. Okay, if we neglect noise. In the anti-correlated case, it's in the different way right here. So you get only 0, 1 and 1, 0 as multiple qubit states. And the point is that you can let then A or B travel in space, and the entangled qubits at different locations are still entangled. That's the point there. And it's a little bit open question to physics. The phenomena appears to happen instantly, ignoring speed of light. No? If you measure, then the other state also collapses. And you also can collapse B. Maybe I forget to tell you, you can also collapse B, measure B and then collapse this A in the same way. But you can also have succeeding operation on the entangled qubits, which do not change the state of the other entangled qubits if the operation is not a measurement. Then both collapse according to the certain probabilities. Okay, and with this we can do many computations. There's a lot of magic outsides and a lot of maybe some thinking of computer scientists especially, which think, okay, we can have always exponential speed up with quantum computers. That's not true, because it's a little bit more complicated. But you can do, for example, all the things you can do in the digital circuit, you can do also in the quantum circuit. You have the quantum logic gates for it. For example, you can have a full adder right here, also as quantum circuit. It's given here. And you might know a full adder, there you have inputs and a carry bit. And you get the sum of the inputs plus a carry bit right here of the output. So for example, 0, 0, 0 becomes 0, 0, that's clear. If you have 0, 1, 0, you will get 0, 1, so the sum is 1. Only if all are 1, then also the sum is 1 and also the carry bit is 1. And with the quantum circuits, you can do the same with the base states, 0 and 1. But you can do also more complicated things. Like, for example, you can have an equal superposition of 0 and 1 as input in A. Have the anti-correlated base state in B. So that means if we have 0 for A, then you will measure 1 for B. And if you have 1 for A, then you will have 0 for B. And we have a carry bit maybe 0. And definitely, because it's anti-correlated pattern, you get then the carry bit 0 and the sum will be in the base state 1 right here. And maybe in this way you understand a little bit better quantum computing right here. It's a huge trend. It's a hype, you could say. There's an exponential growth of the number of qubits. Every year there are new quantum computers in the moment. The current quantum computer with the most number of qubits is IBM Osprey with 433 qubits. Of course, the number of qubits is not all, because there's a limit also on the quantum circuit depths right here, which you can process in the moment. And there we are still very limited. So I think they didn't give these details out for IBM Osprey. But for other quantum computers, we know that the quantum circuit depth is maybe something like 20 or 25. So you can, at most, you can do something like 20 or a little bit above quantum operations, quantum logic gates operations right there. That's it in the moment, but there are also ideas to overcome it, and maybe we'll see it somewhere, hopefully in the end of the decade, where Google at least says, okay, then we will have a quantum computer with 10,000 qubits ready and working. Okay, quantum annealing is another type of quantum computer. There we already have something like 5,000 qubits. but it's not universal quantum computing. And we have some room temperature quantum computers, even that most are cooled down, cost much energy, but here. But for example, D-Wave has some room temperature quantum computer, in the moment 5 qubits, but in the middle of the decade, they also want to be 50 qubits, and in the moment it's something the size of a server rack, and they promise to, or have the vision to reduce the size to the size of a GPU card. Okay, I said there's a lot of noise right here. And that limits this quantum circuit depths where you can do meaningful operations with it. So we are in the area of the noisy intermediate scale quantum computers in the NISQ area. And there is a vision, and Google, IBM already worked for it for some time, and still working on it to get the fault-tolerant quantum computer right there, where you don't have this limit of the circuit depths right here. And there's a strong theory that it will work in practice. They even know, okay, which properties I must get to solve this problem right here. Okay. And it's like this, okay, if you're below an error correction threshold, then you have done it. Then you have fault-tolerant quantum computing. And the potential of quantum algorithms is quite high. So, for example, there's collections of quantum algorithms right here. For example, the quantum algorithm zoo is there, where they investigated something 400 something references, examined 64 algorithms, and they see that, okay, 31 have a super polynomial speed up. That means almost exponential speed up. It's quite much. Only polynomial speed up are 27, but there are many, many problems right here, which until now only polynomial, something like quadratic speed up is possible. It's known that there are these kind of algorithms. Exponential speed ups are for practical applications not so often, but the quadratic speed up is already quite much. And there are famous quantum algorithms. For example, Shor's algorithm is there, with which you can factorize in prime numbers, which is known that this is extremely hard for classical computers. Okay, maybe 1290 to get the prime numbers of it is also not very hard, but if you have very large numbers, then it will become very hard and hard thing to do. And if the prime numbers here are also very, very big. And we can see, because there is a pattern in the some regular pattern which you can use and use some interference in quantum computing, you can get then some super polynomial speed up. So as I said, you can factor integers in polynomial time. And of course, this is important for cryptography, something like RSA algorithms and so on, right there, which are based on integer factorization, that this is a hard problem. There we will have some problem, So we come to post-quantum cryptography right here, where already many researchers find out some algorithms which are still suitable for after we have quantum computers where we still have same safe security protocols. The other basic algorithm is Groove search. There you can just have some black box function as input to Groove search algorithm. This black box function the input is just the number of a given domain, something, and it returns true and false. And Groove search algorithm finds one X inside the domain such that Fx is true. So it does exhaustive searches. It doesn't know anything about the black box function. It does exhaustive searches. And what we can see is that we have a quadratic speed up. And by the way, it also has some impact on cryptography because for many protocols, you now must have something like the double number of digits. So it must be the keys must have double size because especially because you can use Groove search algorithms such that it will be still safe if you have quantum computers right here. And this Groove search algorithm is the basis of many other quantum algorithms and applications, which we also see later on. So now I dive into the basics. I hope you could follow me for these basics, but they are quite important. It's a very short time, and typically the basics are maybe the basics are given maybe in some lecture. I can also provide you the link to the quantum computer lecture right here after my talk. And quantum data management now asks the question, two questions: what can data management do for quantum computing, and what can quantum computing do for data management? And for the first, right here, we can have the vision of a database management system. We can also adapt it to machine learning at some point. And it would be good if we can, within the database management system, offer an easy access to quantum computing applications by integrating high-level functionalities for quantum computing applications. We can extend, or for this purpose, we should extend the query language to call quantum computing subroutines. It would be good if we can easily store and access the input and output of quantum computing applications in the database management system. It would be good if we can automatically choose the needed and viable quantum resources, as well as apply hybrid algorithms and tailor it in a way that missing resources in support of qubits and circuit depths in quantum computers are overcome by taking more computation by classical algorithms or simulations of quantum computing on classical hardware. So some type of hybrid algorithm right here. Details about my talk, and especially about quantum data management, including references, are also given in a paper, a Keynote paper, which is also published in the proceedings right here, with the same name as the Keynote talk. Now we can also ask actually for quantum machine learning. So there's a trend, of course, everywhere is a trend to apply machine learning everywhere, but there's also a trend in the database community such that database management systems offer machine learning functionalities. And there we have additional requirements, like we must have scalable training, where large-scale data sets are processed in comparison to the often simple and efficient to perform application prediction phase. We want to store models and the parameters after training for the use in the application and prediction phase. Right there, we have additional language constructs for expressing complex machine learning tasks in a simple way while combining these language constructs with query languages. We want to automatically choose and optimize models and machine learning tasks. And the open challenge right here is that we now look at quantum machine learning and adapt the requirements and solutions to quantum machine learning. And also consider the available quantum computers with an additional focus on hybrid algorithms. Where hybrid algorithms combine a quantum algorithm with classical algorithm, I already pointed out, such that we can automatically adapt to the viable system configuration of classical and quantum hardware. So, the other direction is, of course, also very, very interesting, and I will give further details on it right here. So we can also think about what can quantum computing do for data management, and there one thing is that we can speed up some tasks of data management with high runtime complexity in order to speed up them. So I give two examples, optimizing queries and transaction schedules. I hope I still have time such that I can give the full 1 hour talk right here because of the delay. So, the point is now, this is maybe some architecture for using quantum computers within database management systems. And here we see, okay, we have clients and they submit queries or maybe whole transactions. And okay, Sachi is calling me. Hi, Sachi. I didn't understand you. Okay, waiting. So something until okay, very fine. Then I will go on just with the talk. Very good, because there's much to talk about it. Thank you very much. See you. Okay, I'm sorry that we have this way of communicating with telephone with each other, which sometimes doesn't lower the barrier for communication right here. We have the queries and transactions submitted by the clients to a database server. And now we use the quantum computer as hardware isolator. We could also use FPGAs, GPUs, and so on, or normal multi-core CPU. But now the thing is that we investigate to use a quantum computer as hardware isolator. And of course, not all problems can be solved with quantum computers. It's not suitable for it. And we optimize the query and transaction schedule on it, and then process the query, the optimized query and the optimized transaction schedule on the classical CPU. That's here the architecture. We can show there already some results. And what we can see is, okay, what are the problems which we consider? One is query optimization, and in particular join order optimization right there. That means, okay, maybe you know SQL queries, they have joins inside. And the join order has an impact on the overall processing time. That's the point there. Because some join orders produce less intermediate results than the other. Or maybe you can use other join algorithms or something like that. And for the transaction schedule optimization, you have transactions. Some of them block each other. And you assign them to the cores of a multi-core CPU. Here we have 3 cores. It's very unusual, I know, but for simplicity of presentation. And you arrange them in that way, so you have also, or can estimate the length of a transaction. So you arrange them in that way that you have a minimal make span right here. Minimal processing time of all the transactions. And you additionally consider that 2 transactions run in parallel, that they don't block each other. It doesn't look so complicated, but that are already hard problems right here. And there is a literature where you can use many different approaches for it, mathematical optimization approaches, like dynamic programming, linear programming, random walk, simulated annealing, machine learning, genetic algorithms, and much more right here. And we already integrated some of the optimization approaches right here in an open source relational database management system and PostgreSQL right here. So we are already running these optimizations right there within the database management systems, at least for query optimization. Okay, here are the algorithms, and they are used in query optimization. So here's a query optimization approach that very often has some basic algorithm. Yes, we have some list, but it can be extended. And you have the quantum computer counterpart for the basic algorithm. So the straightforward way would be to just replace the basic algorithm with the quantum computer computing counterpart and integrate it into the database management system and look the result right here. So one approach is using machine learning for join order optimization. And what we already have done is that we use quantum machine learning for join order optimization. For quantum machine learning, you just implement the model right here and the prediction calculation based on the model with the quantum circuit. And you have some, of course, some parameters which you optimize the quantum circuit. The input data must be first encoded, then you can apply the model, and then you can do the measurement and get the predicted join order. If we, here's the quantum circuits which we use. You have some rotations according to some axes, y, z, and maybe also x. And the angle of the rotation right here, there you have the different parameters which you later on optimize during the learning phase, and you have an entanglement layer. So these are variational quantum circuits, and they are most often used, and they already work in the NISQ quantum computers. That's the point. In the current state of the art quantum computers. You have an entanglement layer, I already showed that you can have a linear entanglement layer, but also circular, fully connected, and so on. There are different versions for it. But overall, we already have some experience with it, and we can show, for example, here on the y-axis we have a reward, which shows the quality of the predicted join order in comparison to the best join order in terms of execution time. One is the best right here. And we can show, okay, the classical machine learning is quite worse. We need, some layers for the variational quantum circuits, but then we can compete here the hidden layer. And we also did experiments with other classical approaches, for example, genetic algorithms. We are also better than the genetic algorithm, which is integrated in PostgreSQL, but cannot reach dynamic programming, for example, which is an exact algorithm. But maybe there are failures because of estimations in dynamic programming. So this was used with the Adam optimizer. So Adam optimizer was used for the optimizing right here. There we have a good result for 8 layers. If you use other optimizers like SGD, we can get even a little bit better. But then it's clear that more layers have also a better result right here. So for SGD optimizers, we have with 20 layers, we have somehow the best result. So more layers is better, but on the other hand, we only did simulations right here, and 20 layers will not work on a quantum computer in the state of the art. There's a pity, so maybe we know already that future quantum computers will definitely beat classical machine learning right there. There are also other literature which shows that classical machine learning or that quantum machine learning can, for example, learn on fewer training data, so you need less training data to achieve the same. Or you can learn faster, that we cannot see here, but we can get better results. So open challenges, of course, are, for example, what should be the properties of quantum computers, like number of qubits, latencies of gates to achieve certain speed ups. We have some preliminary results right there. How to combine further classical and quantum computing algorithms to achieve good speed ups with few qubits. And what other database domains besides query and transaction schedule optimization benefit from quantum computers? Okay, we can have a literature review, for example, about machine learning tasks where it is everywhere applied in databases, and that might be a starting point for future work right here. Our results are done in the QC4DB project about accelerating relational database management system via quantum computing. It's funded by BMBF, 3 years, 1.8 million euros is the volume. And we are a partner, and we are the coordinator of this project, and Quantum Brilliance is another partner. I already talked about the room temperature quantum computers of Quantum Brilliance. And of course, if you are interested in collaboration, just contact me. You can look for some future work on it. Okay, this I will jump over. Now we will look at transaction schedule optimization. We will first point out quantum annealing for transaction schedule optimization, where clients send transactions to the database management server, and the transaction schedule is optimized on the quantum annealer. Afterwards, the classical CPU processes the transaction. We consider pre-claiming of locks to avoid deadlocks, and holding all locks until end of transaction, transactions, yeah, which is some variant of the two-phase locking protocol right here. It's a strict conservative 2PL. And if you look at optimizing transaction schedules, you could say that's a variant of job-job scheduling problem. I already explained it to you. You must assign the transactions to the cores of a multi-core CPU to get a minimal time span. Blocking transactions, yeah, should not run in parallel right here. And that is additional requirement to the job-job schedule problem. And of course, yeah, the job-job schedule problem is also a little bit differently formulated right here, defined. But it's very much related. Okay, we use quantum annealing for it, which just as a result of the optimal. Okay, I see there's some other video right there. So such that we have the minimal, the global minimum. We determine the global minimum of cost function right here, and we must define the cost function for the transaction schedule optimization. That is our purpose right here. That is our problem which we must solve. And for this, we define a transaction model. And what you can see is on a quantum annealer, you can solve quadratic unconstrained binary optimization problems. And they are defined like this, that you have n weighted binary variables. So these binary variables can be 0 or 1, and they are weighted in linear or quadratic terms, and all this must be minimized. So for xy, you have a weight vi, and for combination of xi and xj, you have also some weight right here. And overall, if you put the sums of these weights and combinations right here together, then you get, then this formula will be optimized by the quantum annealing. And if you look at our transaction schedule optimization, we define it like this, that we have a lot of binary variables. And for example, the meaning is that for xijs, if that is 1, that is the case if and only if the transaction Ti is started at time S on machine Mj and otherwise 0. So for example, this xv12, there we have the transaction T3 is started at time 1 on machine 2. So this is this transaction right here. Okay, and we see, okay, we can have a mapping to the assignment of the transactions to the thing right here. Okay, I guess I must come now to an end.
Hi, Sven.
Hi, Sachi. Should I come to an end now? Yeah. I will come shortly. You see the slide number. I will shorten it. What's now? So I have another 5 minutes, or I don't have another 5 minutes? Yeah. Okay. I will finish now. So no problem. See you right then. So sorry for the delay. first I get to know, okay, or understood that I have some time left, but I definitely wanted to stop somehow about here, so that those who are hungry go to lunch right here. I just wanted to show, okay, we can formulate the optimization transaction schedule problem as quadratic binary optimization problem, something like a formula you must have for each transaction start exactly once. Transactions cannot be executed at the same time on the same machine. Transactions that block each other cannot be executed at the same time. There are a lot of details right here, which I cannot dive into it, but it's published. You can look at the papers. We must have another part which minimizes the maximum execution time, where we have increasing weights. So weight of steps n is larger than of all preceding steps 1 to n minus 1. So it prefers transactions ending earlier. And if we go for it, we get some solutions, and we can run it on a real quantum computer. So the first minute is for all for free. You're invited also to check it out. And afterwards, it costs much money. And we can see, okay, for quantum annealing, we have always the constant type, as long as it fits on the quantum annealer, we have constant time and get the optimal solution out of it. We have some pre-processing time, which increases. That's maybe a problem. But for simulated annealing, it's also increasing time. Okay. And then we can go on, and we can solve it on a real quantum computer. I will skip optimizing the transaction school via a universal quantum computer right here, which uses Groover search. There, the main point is that you can also look for suboptimal solutions and have better runtimes, such that I can finish that you get now the basics of quantum computing. I hope you could follow and get some idea about what quantum computing is about. And I gave 2 examples of quantum computing within data management right here to solve data management problems. For example, optimizing the join order right here, which we solved with quantum machine learning. And the other thing was that we optimized the transaction schedule optimization problem, where transactions are assigned to the cores of a multi-core CPU and are not blocking each other. And we definitely have some speed up right here, and there's still a lot of things to do, a lot of future work. If you are interested in collaborative work right here with us on these or other topics, just contact me. I guess you can find out the contact details right here. I can also in the WhatsApp group, I already sent around the slides. Right here, the links to the slides. I will also send you a link to my quantum computer lecture. The slides are online available for free, and also my contact details. So, yeah, I guess it's not possible to have some questions at least, or only from them which are viable here online.
Okay,
So,
Professor Sven, so
yeah,
I have no words to tell thanks. So in early morning,
Thanks.
6 o'clock, you wake up and start the preparation. So I like to thanks how to, any question from audience side? Any question from audience side? So I have a few questions, so let me ask, because without question I will conclude, then it will not good, right? So how to interaction between the qubitings and the environment?
the qubit thing, and the other I didn't understand
Yeah.
acoustically.
How to communicate among them, qubitting?
Communicate between qubit and what?
Yeah.
Qubit and what else? So the qubits, you have the quantum circuit right here,
Yeah. This.
where you have here the qubits, and then you have the operations on them. So you can, you have some multi-qubit operations. And of course, if you mean the communication from the classical world to the quantum computing, there you can first set some quantum state and do then some quantum operations, and later on here you do the measurement, to get the result.
Yeah, I got it. Thank you. Thanks a lot. Please give the big hand for the Dr. Sesum.
Yeah, thank you
Yeah,
very
thank
much.
So you will get the
Thank you
review
very much.
certificate and your Keynote certificate. Right now I will sending to you your email ID. Okay. Thank you.
Yeah, thank
Okay,
you very
thank you.
much for the for opportunity to have a keynote speak at your prestigious conference right here. Greetings to Sachi and all the other organizers right here. They are doing a good job. Have a good lunch.
Okay.
And
Have a-
hopefully see you
Thank you.
one
thank
time.
you. Thanks a lot. Okay.
Bye-bye.
A small announcement. The venue for lunch for participants and authors is in canteen, and for session chairs and